I belong to the region of Punjab in the subcontinent. This is one of the most fertile regions in the world. The name Punjab is comprised of two words, Panj meaning five and Ab meaning water. The land of five waters, the land of five rivers. And these are not tiny ponds around the corner. Each one of them is more than 300 miles in length. But we have a saying in Punjab which roughly translates to even if you are standing next to the river, do not waste water. This is the overarching theme for this course, specifically designed for scarcity in a world of abundance. Even if the resources in the cloud seem infinite, we should always try to use less resources whenever possible. My name is Fawad Qureshi, and I've been working in the cloud data analytics space for 2 decades. In this course, you will learn the fundamentals of cloud sustainability. We'll cover what makes some technologies greener than others. I'll show you some common carbon measurements and their implications. And finally, we'll talk about how consolidation results in a better carbon footprint. If I want you to think about one thing when building your cloud strategy, then you should always remember what Punjab told us. That is, do not waste water. So if you're ready to begin, let's get started. Planet Earth is currently operating at 140% of its capacity and on track to be operating at 200% by the 2030s. Imagine a boat which is safe to travel for a maximum of 10 people at a time, and you find out that the boat is constantly being used by 14 people at the same time. You also hear that people are planning to use the same boat to transfer 20 people at all times in tumultuous waters. Would you be concerned if you're one of the 20 passengers on the boat? This is exactly why you should be concerned as a dweller of the planet. We need to change our ways on how we consume resources on this planet. In the last few years, cloud computing has generated a lot of interest in the market for multiple reasons. Next, we will discuss the sustainability benefits of using the cloud. Accenture, a well known IT services and consulting firm, in their research paper, The Green Behind the Cloud, found out that by moving to the cloud, some companies can save up to 95% of their carbon emissions generated by their on premises infrastructure. This reduction comes from better power and cooling efficiency in public cloud data centers. This follows the same principle like carpooling or public transport over everyone having their own car. You may not drive your own car for more than 2 hours a day on the average, and for the rest of the 22 hours, it is parked outside your home or workplace. Using public transport or carpooling, you are able to spread out the idle time across many consumers. Similarly, if you have your own infrastructure, there would be times it is not utilized, but yet it is running at all times. In the cloud, through the use of multi tenant deployment, you can spread out resources across several consumers. Thereby, on the whole, a country would end up consuming less resources. What drives this efficiency? Accenture's research has shown that, for example, AWS data centers are 3.6 times more energy efficient than as compared to median US enterprise data centers. This delivers a significant improvement in hardware efficiency, which in turn reduces the per CPU unit energy consumption. Further improvement can be achieved by following sustainable software engineering principles and implementing cloud native design patterns. The use of multi tenancy allows several applications to share resources, which reduces energy consumption as compared to when applications are working on dedicated infrastructure. Cloud providers have unique scale and financial incentives and can work closely with stakeholders in adopting the circular economy when it comes to hardware. Accenture estimates show enterprise technology manufacturers can capture an additional 16% of operating profit by designing products for longevity, modularity, and circularity. All of these benefits combined mean that organizations can save up to 95% by moving their data centers to the public cloud. Now that you understand the benefits of the cloud shared economy model, I'm going to show you how your business can leverage the cloud for more efficiency. This process starts by measuring your business's carbon footprint, which we will cover next. So, you have been given the task of measuring the carbon footprint of your IT estate in the cloud. Where do you begin? If you want to examine the impact of carbon consumption in the cloud, I would suggest beginning with the data analytics workloads, which are some of the most demanding workloads in the cloud. Here are five things which are critical to review and manage. The first three are in control of the cloud service provider. Energy source. Select a clean energy source, for example, renewable energy such as wind and solar over coal. Overall usage. Make sure the overall usage of the data center is well controlled. This is usually done by having effective cooling practices in the data center to reduce energy wastage. These practices include having effective airflow management, consolidating light running servers, and reducing the overall number of hardware in the data center. Standby power. Ensuring that the standby power consumption is not too high when the systems are not running any workloads. This is done by selecting hardware manufacturers in your data center with a greener idle footprint. You can get details of energy consumption by CPU rates through organizations such as Spec Power, which we will learn about in the coming sections. The next two are in control of the application designer in the cloud. The first has to do with system utilization, and it is important to make sure you're saturating your existing resources before adding more to the current configuration. We must fully consume all resources before starting to add more hardware to solve problems. The next point is housekeeping. What does this mean? This means what are you doing to ensure that you are a good tenant in the cloud? Are you releasing the resources back to the cloud service provider? Or are you keeping them in a hot pool of resources like some of the multi tenant applications do? Single tenant carbon accounting is simple. All the resources are only provisioned for you, hence, all the carbon is allocated to your organization. Some single tenant applications will over configure their resources in case there is a spike in the workload. Any carbon for extra resources are also 100% allocated to the single user of the platform. It gets complicated in the multi tenant scenario. Multiple users are sharing the infrastructure. Multiple tenant applications usually maintain a set of resources on hot standby, often referred to as the hot pool, provide you access to additional resources in scenarios such as autoscale, pause, resume, etc. to deliver on their service level goals. Now imagine if there are 100 customers in one region, each consuming on an average 5 nodes, and there is a hot pool of another 200 nodes available. From a carbon calculation point of view, for each customer, are they responsible for the 5 nodes they are consuming? Must there be appropriate allocation done for all the 200 spare nodes? Meaning, from a carbon perspective, each customer must report 7 nodes worth of carbon. Normally, the resource split between multiple users is much more complicated, and this is a simplified view of the problem. Most of the industry today only allocates the carbon used by the user to them, and the hot pool is the responsibility of the service provider. This ensures that there is an incentive for the provider to manage it down and reduce the wastage. So, in the previous example, you will only account for 5 nodes per user instead of 7. For a simpler example, the logic would follow that if I go to a retailer, I'm only responsible for the carbon pollution caused by items I buy and not for the inventory of the store that the retailer is maintaining. As a consumer, you should make informed choices and select service providers who do a good job of managing their resources in the cloud. In general, efficient multi tenant applications will consume less energy as compared to single tenant applications on the average. Now that you have understood the 5 basic factors which drive energy consumption in the cloud, next we will talk about the types of emissions and under which category do you need to report the emissions generated from the cloud. It is difficult to know where to begin tracking your business's emissions without knowing what is the direct or indirect consumption of your business. There's a regulatory framework to divide your carbon emissions into 3 main categories. Scope 1 are all direct emissions. This means all direct emissions from the activities of your organization or under its control, including fuel consumption on site like gas boilers, fleet vehicles, and air conditioning leaks. Scope 2 are indirect emissions. What emissions are occurring from utilities purchased and used by the organization? Emissions are created during the production of the energy and eventually used by the organization. Scope 3 are all other indirect emissions. These are emissions from activities of the organization, occurring from sources that they do not own nor control. These are usually the greatest share of the carbon footprint, covering emissions from business travel, procurement, waste, and water, to name a few. Scope 1 and 2 are easier to manage for an organization. Scope 3 emissions, which sometimes make up to 80 to 90% of an organization total emission, can be a challenge to accurately predict and report. It requires close data collaboration between your partners, suppliers, and other stakeholders in the business. Please keep in mind that under current regulations, all the carbon emissions from your own premises data center is considered Scope 1, while if you move all the workload to the public cloud, it will be considered Scope 3 from a carbon reporting perspective. In this section, we talked about different types of emissions and how most of the emissions for an organization fall under Scope 3, including emissions generated from cloud computing. Next, we will dive a little deeper into how the carbon consumption of a computer changes with its utilization. Have you ever thought about how your smartphone has battery ratings of 6 hours for talk time and 48 hours for standby time? This is because when you are making a call, the phone is doing more grunt work and thus requires more power to complete the tasks. Similarly, the power consumption of a computer doesn't remain the same all the time. As you put your machine under different levels of stress, its power consumption will change over a period of time. For example, if you're watching a movie on your laptop, it may be running at 40% CPU utilization. However, when the laptop is just turned on and no applications are running other than the operating system, then it might only require a small percentage of CPU utilization and less power. The Standard Performance Evaluation Corporation, SPEC, is an American nonprofit corporation that aims to produce, establish, maintain, and endorse a standardized set of performance benchmarks for computers. The increasing demand for energy efficient IT equipment has resulted in the need for power and performance benchmarks. In response, the SPEC community established the SPEC Power Community, an initiative to augment existing or create new industry standard benchmarks and tools with a power energy measurement. On the slide, you can see a sample benchmark for spec power for one server, and you can see how the power consumption of the node changes for each 10% increment in CPU utilization. From the chart, you can see that one computer running at 80% CPU will consume less electricity than two computers of the same type running at 40% each. This is clear evidence that supports using less resources in the cloud to optimize energy resources. Not only would you end up consuming more power for two servers instead of one, imagine if every workload starts using two nodes instead of one. What do you think the outcome would be? You would require a much bigger data center, which would also increase the cooling cost of the overall infrastructure. Now, you understand what happens to the power consumption when you increase CPU utilization, and more importantly, how the power consumption goes up when you use two nodes instead of one. We also learned that more nodes means higher cooling cost. In the next section, we will dig deeper into the total data center power consumption and how it is measured. What happens when you buy more electronics for your home? Of course, your electricity usage increases, but imagine your house no longer has space for the incoming electronics. So, what will you do? Do you try to manage the influx of new gadgets with your existing electronics, organizing them like a game of Tetris? If that's not possible, do you move to a bigger house? The bigger house will be more expensive in several ways. The taxes would be higher, the cooling cost would be higher, you would need more equipment to support it, etc. Similarly, the growth in cloud computing means that the cloud service providers have to continuously expand and move to new, bigger data centers all the time. The same thing happens in the large data centers. The cloud service providers try to manage the cooling in different ways. They introduce better airflow mechanism, moving to a colder area using renewable energy sources, etc. Power usage effectiveness, or PUE, is a measure of how good a company is managing the cooling of its infrastructure. PUE is a ratio of total energy consumed by a data center divided by the total energy consumed by servers and computer hardware. The best case scenario is a ratio of 1, which means the data center requires zero cooling, which is nearly impossible. Ideally, the ratio should be close to 1. Google had a PUE of 1.1 in 2019, which was pretty remarkable. When you are selecting a cloud service provider region, you should always ask for the PUE. This will ensure you are choosing a provider that is doing what they can to conserve energy and lower their carbon footprint. So, in this section, we discussed PUE and how it gives you an indicator of power management practices of a cloud provider. We should strive to have a PUE ratio closer to 1. Now, in the next section, we will discuss the different cloud shared responsibility models and if it has any impact on power consumption. Have you heard terms like infrastructure as a service, platform as a service, or serverless, etc.? Does serverless mean that there is actually no server? That's not true. The term serverless refers to an illusion that since you're not managing the server yourself, that it isn't there at all. But the reality is that the server is hidden from you and you just focus on your application. The different terms you hear like IaaS, PaaS, serverless, and SaaS are just terms that refer to a shared responsibility model, meaning that there are varying parts of a full technology stack that are visible to you and you have full responsibility to manage the architecture. In terms of computer resources, every component is still required, just like you would in an on-premises or a full stack model. There is no difference in what needs to be managed, just who does it. Serverless does not mean there is no server. It just implies the provisioning of those resources is hidden from you. As examples, Salesforce, the popular CRM tool, is a SaaS offering. AWS Lambda, Microsoft Azure Functions are examples of serverless tools. AWS Beanstalk is a good example of PaaS, while AWS EC2 is an example of infrastructure as a service. From a carbon consumption perspective, you must add up the energy consumed by those hidden resources. Sometimes it will be a challenge because the true as a service providers do not share the underlying infrastructure details with the customers. We will talk about how can we estimate those carbon numbers later in the course. So in this section, we discuss the different cloud shared responsibility models, and despite some of their names, all computing resources are part of the deployment, which means we must count the power consumption of those resources for carbon reporting. Next, we will discuss how we need to be mindful of some cloud vendors throwing infrastructure to overcome their software limitations in the cloud. When resources are abundant, it is very easy to be lulled into a false sense of security and be less mindful of the available resources. Remember what Punjab taught us in the introduction movie, that even if you have hundreds of miles long rivers, do not waste water. Autoscaling is a cloud design pattern where you can seamlessly provision or allocate resources as the user demand increases. There's nothing wrong in using more resources when it is justified, but sometimes we see that vendors try to use autoscaling to overcome the software limitations by adding extra hardware to compensate for software inefficiency. This phenomena was demonstrated by an academic research paper from Carnegie Mellon University, a leading software engineering institute, showing that throwing infrastructure at a software problem results in much more resources being consumed than as compared to if you had an optimized software. In their research paper titled To Autoscale or Not to Autoscale, they took an optimized system and compared it with a suboptimal system with an autoscaling enabled. Their conclusion was our results show that autoscaling works well. In fact, so well that we were able to take a system with obvious architectural flaws and make it perform nearly as well as a fully optimized version. However, hiding these efficiencies comes with the price of additional infrastructure. In our case, our inefficient baseline configuration required up to 8 times the resources of our efficient optimized configuration to achieve comparable performance. This will not only be more expensive from cloud billing perspective, but your carbon consumption would be several times higher. Please keep in mind some vendors may not pass down the cost of the extra hardware since they are in the growth stage of their business and want to acquire new customers at all costs. This is not a sustainable business practice. So you should be wary of software vendors using design patterns such as autoscaling to hide inefficiencies in the cloud. You cannot throw hardware at a software problem. We talked about how in 2010, the Earth was operating at 140% of its resource capacity, and we are on track to be operating at 200% of the resource capacity by 2030. We simply should not condone this behavior by vendors who are throwing hardware at a software problem. In this section, we learned that by using the cloud design patterns incorrectly, not only can you generate unnecessary carbon for the same workload, but that this can be fixed by using the appropriate software development practices. Next, we will talk about these software development practices, which will help you in delivering an energy efficient software. Since the world has reopened after the pandemic, we see that the airports are getting a lot busier. Let's take an example from an airport arrival terminal. Imagine you land at an airport and you have to move your luggage to the taxi rank from the baggage carousel. Imagine it takes one person 1 minute to move a load with a rolling baggage carrier or trolley. If you have one trolley or baggage carrier, for 10 people, it will take 10 minutes to complete with each person sharing the single trolley. This is serial processing. If you have 10 trolleys for 10 people, now it will only take 1 minute to complete the task. This achieves the maximum parallel efficiency of 10x. If 5 people insist of using the same red trolley, which means they would have to do their task in sequence. No matter how many free trolleys are available, it will always take 5 minutes to complete the task. This results in a maximum parallel efficiency of 2x despite the fact there are idle resources available. Why are some technologies more optimized than others? Parallel processing is the single biggest driver of compute efficiency. This means that if your solution is able to make use of more resources, trolleys in this case, at the same time, you will get your work done quicker. This is known as Amdahl's law in computing, which is the law of parallel processing. The law states that your parallel efficiency is determined by the bottlenecks. If you have no bottlenecks, then you can get 10x efficiency with 10 trolleys. If you have a bottleneck, which in this case was 5 people insisting on a red trolley, then your parallel efficiency will not improve with the increasing number of available resources. Here is an example of 3 different types of databases processing SQL. Imagine we have 100 terabytes of data to analyze. On the left is a serial processing database. It chugs along at the speed of a single server. Usually there is only one CPU on that server. It is the slowest method. It is like having a single trolley for everyone at the airport. In the middle, we see some parallel processing where multiple servers work in tandem to do the table scans, joins, sorting, and operations. It doesn't do sorting in parallel, and that's a huge bottleneck in performance when terabytes of data are involved. This is like a few people insisting on the red trolley. This means that there are resources waiting in idle to increase efficiency. On the far right is the maximum efficiency system, which does everything in parallel as much as possible. This will be the fastest solution, and to go faster, we simply add more servers to the cluster. In short, the more parallel efficient your systems are, the more you remove bottlenecks and increase throughput. So we learned in this session that a software having no bottlenecks will deliver the best performance and throughput, which also helps deliver better power consumption as either it will do the job in less number of nodes or be done with work much faster than the other solutions. Next, we will talk about what are the implications of carbon measurements on a business. In 1972, the Organization for Economic Cooperation and Development (OECD) adopted the polluter pays principle as a guiding principle. 3 years later, PPP was adopted by European Community. The polluter pays principle is a simple principle based on common sense, and it says the polluter, the actors or the activity causing the pollution should pay to right the wrong. Several countries in Europe have already applied carbon taxes, while the US is slightly behind in its implementation. However, several US based global businesses are already impacted by these regulations. We see typically across Western Europe, the price of carbon ton is nearly $50. We see that Microsoft has only allocated $15 per carbon ton in their net neutral carbon pledge. This could become a problem very quickly if companies do not correctly handle their carbon emissions. We see that Sweden and Switzerland have the highest carbon tax rates of $130 per carbon ton in Europe, as per this World Bank data. It should be noted, however, some countries have high taxes, but their energy generation is very clean. We can take a closer look at this relationship by calculating the carbon intensity for each country. We do this by measuring the amount of greenhouse gases emitted per unit of electricity produced. However, while calculating carbon intensity can highlight some areas of improvement, if we normalize the carbon taxes across Western Europe, we see a different story develop. Here we are normalizing the carbon tax rates on a ton for ton basis. Some countries have a lower carbon tax rate, but their energy generation isn't very clean. So, if we were to look at how much tax you would pay for consuming roughly 39 megawatts in each country across Western Europe, then Netherlands and Ireland turn out to be the most expensive as they have the worst carbon intensity. Often cloud users choose Amsterdam region for its high internet speeds, but this would be another dimension to look into while selecting a cloud region. The EU has an emission trading system where each industry or organization is given a maximum cap of carbon. The overall volume of greenhouse gases that can be emitted by power plants, industry factories, and aviation sector covered by the EU emission trading systems (ETS) is limited by a cap on the number of emission allowances. Within the cap, companies receive or buy emission allowances which they can trade as needed. The cap decreases every year, ensuring that total emissions fall. So, if you do well with your carbon goals, you can sell your carbon credits to other companies. Or if you run over, then you must buy credits. To recap, in this section, we learned about carbon tax rates, carbon intensity, and how companies can trade their carbon credits under the EU ETS system. Next, we will talk about the carbon calculators provided by the cloud service providers and how you can use them for carbon reporting. Examining cloud service provider emissions data is almost like getting an aggregated bill from your mobile provider with limited line by line items. There is very little breakdown of how the costs were calculated. While all the CSPs do share the data for greenhouse gases, they are in aggregated form and it is not possible to compare different technologies and fully understand bottom up numbers which could guide you in making corrective decisions. But still, you can use this data for top down reporting of your company's total carbon emission generated by cloud computing. We could use the calculators in creative ways to calculate per service per node carbon emissions. Here's how. All the cloud service providers have a carbon calculator, but they only provide emissions at a monthly level. If you want to use it for a benchmark comparison, then one option could be that you use a clean CSP account and run the benchmark on technology 1 at the end of a month, let's say June, and nothing else in the month of June using that account. The total emission in the month of June, as per the calculator, would be the approximate total emission for technology 1. For technology 2, you can start your test in July and similarly run nothing else on that account in July. This way, the total emissions of July, as per the calculator, would be for technology 2. So, we learned in this section that you can get aggregated data from the cloud service providers, carbon calculators, and with some creative planning, you may be able to get service level data from those calculators. Next, we will talk about another method using golden coefficients to estimate power utilization. Etsy is an online crafter marketplace, and their team has built different solutions in the cloud. They've done some benchmarking to estimate electricity consumption on a per unit basis. If you want to use some rule of thumb assumptions for calculation, then you can follow the golden coefficients built by the Etsy Cloud team. They call them Etsy Cloud Joules. In their tests, they have demonstrated that one vCPU in the cloud typically consumes 2.1 watts per hour, 1 terabyte of hard disk drive consumes 0.89 watts per hour, and 1 terabyte of solid state drive consumes 1.52 watts per hour. So if you have the infrastructure details, you can use these coefficients to build your energy estimates. You may have some error percentages, but in the absence of detailed carbon data from the cloud service providers, these golden coefficients can help in calculating and estimating power consumption. In this section, we learned about a power estimation mechanism, and in the next section, we will apply it on a couple of scenarios. Let's take the example of a time trial. Two technologies are required to complete 100,000 tasks in 30 minutes, starting with 3 nodes of similar type each. Technology A completes only 35,000 tasks in 30 minutes, and when we double the servers for technology A, it only completes 45,000 tasks. Does this remind you of the airport example from earlier in the course? It looks very similar to the red trolley problem, which indicates some inefficiency in this technology.
Technology B easily completes the task with 101,000 queries in 30 minutes using 3 nodes. Next slide. Since technology A didn't complete the task, we linearly extrapolated and determined it would take about 12 nodes for technology A to complete the task. Hence, the energy consumption of the 12 nodes of technology A is compared with 3 nodes of technology B. We are assuming 60% CPU utilization with an average of 235 watts per hour consumed by each server. The detailed calculation can be found in the attached workbook of the course. Using the numbers on the previous slide, we are extrapolating the numbers for a full year. We can see that the annual electricity consumption is 12 megawatts for technology A, which is 4 times that of technology B. But you can say that I don't pay for the electricity. It will be the cloud service provider who is responsible for that. But if we assume 200 grams of carbon dioxide per kilowatt hour, then it will generate 2.47 tons of carbon for technology A as opposed to 0.62 tons of for technology B. Assuming a $50 per carbon tax, we can see that technology A would result in a carbon tax of $123, while technology B will only generate $30 carbon taxes. In this example, we see the electricity consumption comparison between two technologies. One technology met the required goal while the other did not. In the next example, we will apply the same approach to a scenario where both technologies are able to meet the required goal with a slightly different internal configuration. Let's take the example of another time trial. The requirement is to complete 200,000 tasks in 60 minutes. This time, both technologies complete the required task in the same number of nodes with identical results. Now, we will use the energy calculation as per the Etsy Cloud Joules. Although both technologies use 6 nodes to complete the task, technology X had 64 vCPUs per node, while technology Y had 32 virtual CPUs. This resulted in much different total energy utilization. Just like previous example, we have calculated annual electricity cost, carbon emissions, and carbon taxes for technology X and Y as well. As per the charts, you can see that despite having the same number of nodes and achieving similar end results, the carbon taxes of technology X is $109, while technology Y has a carbon taxes of $74 approximately. In this section, we learned that using the similar rates of electricity, carbon intensity, and carbon tax, we can see even when two technologies complete a certain number of tasks in the same number of servers, their internal configurations can result in different carbon emissions. Next, we will discuss how technology consolidation delivers a greener footprint for the enterprise. We talked about how using cloud computing versus on premises computing is analogous to using public transport over private cars. 50 private cars versus 50 people in one bus has dramatically reduced carbon footprint. The carbon reduction is possible because the bus allows for consolidation. On a unit basis, a bus may have higher carbon consumption than one car. You will not get any benefits if 50 people buy 50 buses. Similarly, just because you have moved workloads in the cloud doesn't mean you are getting the full benefits. Many companies sometimes do not focus on broader data governance strategy and keep on adding new technologies to the mix. This not only adds complexity, but it also increases the overall carbon footprint of the organization. You must consolidate your workloads and system in the cloud wherever it makes business sense in order to make greater use of the shared economy model. Consolidation of data and application results in reduction of infrastructure cost by consolidating into a single centralized environment, eliminating risk and cost of multiple fragmented environments, delivering reliable, consistent results based on a common set of agreed upon business rules, eliminating cost and confusion on duplicated data and conflicting results, increasing reuse of data by multiple applications, eliminating cost of duplicating data effort, building new technologies. The defragmentation of technologies allows business to deliver much faster time to value. It reduces the overall infrastructure cost and thereby eliminates unnecessary carbon emissions. We discussed in this session the data and application consolidation in the cloud, which will help you in realizing the full green potential of the cloud. Next, we will talk about where can you learn more about sustainability and what actions can you take in your organization to implement a sustainability strategy. This is my favorite story regarding sustainability. In 2014, British shoppers took 8.5 billion plastic bags which went to landfill. In December 2014, the UK government introduced a 5p surcharge which reduced the number of plastic bags by 85% to only 500 million in 2015. Do not underestimate the value of small savings from the ground up. When you start to add up all those savings, they deliver grand results. Are you willing to find your 5 penny or 5 cents for your business? You should ask your vendors to publish the electricity consumption numbers. Hopefully, we can get to a point where we get to see such stickers in the cloud service providers' marketplaces. Before buying the technology, we'll get to see the carbon emission numbers. These are electricity rating stickers you get for electronics in Europe. The way to read the chart is that technology 1 consumes on an average 4.2 kilowatts per hour when it ran for 1000 hours, while technology 3 consumes 122.6 kilowatts per hour on the average when it runs for 1000 hours. US has different energy stickers for consumer electronics. Here is the same chart in the US Energy Guide format. In this chart, you can see what the estimated annual electricity bill and annual electricity consumption would be for each technology. Technology 1 consumed just over $7,000, while Technology 3 is costing more than $277,000. Each country and geography may have their own version of such energy rating stickers. We have reached the end of the course today, and I would like to thank you for spending this time with me. What we learned today was what are the fundamentals of calculations in the cloud? What are the implications of carbon numbers on a business? And now you should be able to use the methods to calculate carbon utilization for your cloud systems. The key takeaways are: 1. Do not underestimate the small savings at each step of software development. 2. All technologies are not created equal. Efficient use of resources is the single most important factor when it comes to energy consumption. Number 3. For a sustainable future, we cannot keep throwing infrastructure at a software problem. I've added all the resources used in the course in the reference section, which you can go through for further details. Whenever you are working with cloud, remember what Punjab taught us. Whatever you do not waste water. I'm Fawad Qureshi, and I wish you good luck in your journey to save the planet.